So calculus is based on a concept that we call limits. And we've done limits a little bit already when you did geometric sequences. So let's say we'll look at that first sequence there, 8, then 4, then 2, then 1, then 1/2, and so on. Can you see that that's a geometric sequence? That each time you're cutting your numbers in half. We would say that as we get to very, very large values in this sequence, can you see that the term number, and you're probably used to using Tn before, in our IB formula booklets it uses Un, so our term number gets closer and closer and closer to 0. Because if I would walk 8 tiles, then half, 4 tiles, then 2 tiles, then 1 tile, then a half, then a quarter, then an eighth, then a 16th, 32nd, 64th, 128th, 256th, 512th, 1024th. Keep going. You'd eventually get closer and closer and closer and closer to 0. And we learned that with these type of geometric series, if we added them up, we would reach a number. That number that we reach, we would call a limit, because it's the value that we can get arbitrarily close to, but never reach. So each term gets closer and closer to 0, and we can get as close to 0 as we like, because if you said, oh no, you can't get closer than 0.1, well, when you get to 0.1, you cut it in half, you're now closer to 0 than you were before. And if you think, well, you can't get closer than 0.0001, well, when you get there, you cut it in half, and you get closer. So we can get as close to 0 as possible. And because we can get as close to 0 as possible, when you add these up, so if I started 16 away from the wall, and I walked 8, then I walked 4, then I walked 2, then I walked 1, then a half, then a quarter, then an eighth, then a 16th. The amount that I'm adding each time is getting closer and closer to 0. The distance that I'm walking, I'm getting closer and closer to the wall, which I had started 16 away to begin with. So if we added those all up, the sum to infinity would be a limit, and it would equal 16. So some notation here. The arrow means as n goes to infinity, term n, un, goes to 0. So as one gets bigger, the other one gets closer and closer to a value. And then this is where we've walked to the wall. As n goes to infinity, the sum of all those ones goes to 0. And just a reminder, when your r value is between 0 and 1 for positive r values, or 0 and -1 for negative r values, any fraction less than 1, you can use this formula. And for r's, we started with 8. We are always going half. Our formula would tell us it's 16. And we could see through the walking towards the wall that that idea is true as well. Now, anytime you have something that approaches a value, or the limit exists, we call that convergent, because it's approaching something. If it doesn't approach something, we call that divergent. This is what our limit notation is going to look at. We're going to use this, LIM stands for limit, as n goes to infinity of, and this is our formula, or whatever we're looking at. In this case, we're looking at u of n, of those terms in that sequence. So we would say the limit as n goes to infinity of u of n whatever formula we're looking at, is equal to 0. And we could also write the limit of the sums. So we could say the limit as n goes to infinity of the sum of n would equal 16. And if they're not convergent, or if a limit doesn't exist, then we say it's divergent. So here's a sequence. We start with point 2, then point 2, 2, then point 2, 2, 2, then point 2, 2, 2, 2, then point 2, 2, 2, 2, 2, and so on, and past Pizza Hotline and keep on going. Does this get closer and closer to a number? What number does this keep getting closer and closer to? If you did this forever, if you looked at the limit as n gets larger and larger, as n goes to infinity in this sequence, you would eventually get to what number? 0.2 repeating. Because if you keep on going, you just keep getting more and more 2's. Does anybody know what number that is if you didn't write it as a decimal? 2/9. I love repeating decimals. Do you know what 0.1 repeating is? 1/9. 0.3 repeating? 3/9, which is also 1/3. Yes, this. Have I told you the story of 0.9 repeating? No? What's bigger, 0.9 repeating or 1? Right. Your intuition would say, well, 1 is bigger than 0.9 repeating. They are, in fact, the same number. Mathematically, on every test, when your answer is 1, you could have written 0.9 repeated instead. And if you didn't know the repeating sign, you could just keep writing 9s until you're done the test. Okay? Well, I'm going to show you a couple of proofs why 0.9 repeating is equal to 1, just as a little aside, and you can see if you agree or disagree. Proof number 1 is just using a pattern. If 0.1 repeating is 1/9 and 0.2 repeating is 2/9, and you keep on going, well then 0.9 repeating must be 9/9, and so it has to equal 1. I think that's not very convincing as far as it's a pattern, but is it really convincing? So then I'd say, well, let's look at another pattern. Let's take 1/3, which is 0.3 repeating. So I'm going to just imagine all those 3's. And then I'm going to write 1/3 again and 1/3 again. And I'm going to add them all up. I think this might be a little bit more convincing. Now, 1/3 plus 1/3 plus 1/3 is 3/3, which is 1. But on this side, can you see that you can add a column and you never have to worry about carrying over the 1? Because you never get more than 9. And this side would equal all 9's. And no matter how far you went, you would just keep getting 9's. So there's another argument that they would be the same. And one more argument. We're going to do some algebra. Okay? We're going to start by saying x is equal to 0.9 repeating. Okay, that's where we're going to start with. Well, if I had this equation, I could multiply both sides by 10. If you multiply by 10, you'll just move the decimal place over, right? So now I have 10x is equal to 9.9 repeating. If I subtract x on both sides, On this side, I'm going to subtract x. And since x is equal to 0.9 repeating, on this side, I'm going to do the same thing, but I'm going to do it with no number. I'm going to subtract 0.9 repeated on both sides. Well, 10x minus x will equal 9x. And 9.9 repeated minus 0.9 repeated will just be 9. Divide both sides by 9. I get x is equal to 1. But what did I start with? I started with x equal to 0.9 repeating. And I ended with x equal to 1. So they must be the same. Technically, for two numbers to be different, anytime you have two numbers that are different, there will always exist a number in between. Unfortunately, between 0.9 repeated and 1, there is no number in between them. Now, I'm not saying that from now on you do all your math. You know, if you have 5 plus 2 equals 7, you write 4.9 repeated plus 1.9 repeated equals 6.9 repeated, and do all of your math that way. There might be some IB markers out there that'll be like confused by what you're trying to do, or just get annoyed and decide to deduct marks, annoyance marks. So I don't recommend that, but it is an interesting little fact. Okay, sorry. Back to limits and limits of our functions. So again, we have our notation here. We've looked at limits as n, or a value gets very, very large, but we could look at a limit as it approaches a certain value. So here, we're looking what happens to this function as the x values get close to the value of c. And we'll look at some actual numbers. So again, this means limit as x goes to c. Here's our formula, whatever our function is that we're going to be looking at, and it's going to equal the limit. In order for this to work, graphically, it's got to approach the same value whether your x value approaches it from the left side or the right side of your function. So here's our first example. We're just going to look at x squared. We're going to graph x squared quickly. Maybe you remember graphing x squared. The vertex is at 0, 0. Do you remember with parabolas you go over 1, up 1, over 1, up 3, over 1, up 5? Does that ring a bell? Or maybe you just make a table of values, 1, 1, 2, 4, 3, 9, in order to get an accurate graph. Now what happens as your x value gets really close to 2? So what you're looking at is you're looking at, as I go this way, if I'm approaching 2 this way, and I'm approaching 2 from this side, what happens on my graph? Well, if we look at the blue arrow, I mean, this is not supposed to be hard or crazy or anything. The answer is 4. As x gets close to 2, our function is going to get close to 4. But what we're seeing on our graph here is as I get close to 2, along my graph, I'm going up and getting close to that value. That's what's happening as I get close to 2 from the left side. And as I get close to 2 from the right side, both of those values approach 4. So we would say the limit as x gets close to 2 is equal to 4. And as you get closer to 2 from the left, and as you get closer to 2 from the right, both of them approach 4. Now for this function, we could find any limit quite easily. What is the limit as x approaches 3? It's going to be 9, because 3 squared is 9. What's the limit as x approaches negative 2? It's going to be 4. So limits are easy to evaluate if you don't run into a problem. In this case, there are no problems, because any value of x you could plug in. What happens is x approaches 9, the limit would be 81, because you could plug in 9, and 9 squared is 81. So some limits are really easy to figure out because you just can plug in the value. And they're that simple. But sometimes we run into problems. And that problem can be seen right here in our next example. What happens to the limit as x approaches 1? Well, let's just plug it in and find out. And when I plug it in, I get 1 squared minus 1 on top, which is 0. And I get 1 minus 1 on the bottom, which is 0. And 0 divided by 0 is 1, 3? We don't know. So we have to find out what's happening here. So let's go to our values and let's see, does it seem to approach things? Let's fill in our chart. There it is for you. It does seem to approach something. In this case, it looks like 0 divided by 0 is equal to 2. How does that work? Because as we approach 1 from the left side, and as we approach 1 from the right side, it seems that we're getting closer and closer to 2. So we can write this limit as equal to 2. Do you remember how to graph x squared minus 1 over x minus 1? No. This is a graph with a hole in it. How do we, well, if we look at this function, x squared minus 1 over x minus 1, you can tell right away that there's a non-permissible value. X can't equal 1. But the top can be factored. And the top can be factored to x plus 1, x minus 1, divided by x minus 1. And what happens to our x minus 1s? They simplify, and we're just left with x plus 1. And if you're left with just the graph of y equals x plus 1, you get a line. That has a slope of 1 and a y-intercept of 1. But because we had a non-permissible value that x couldn't equal 1, we have a hole. When x is 1, y would be 2 because 1 plus 1 is 2. And we have a hole in our graph at 2. But whether we approach x equals 1 from the left side or we approach it from the right side, our values get closer and closer to 2. All right, that's where we'll end today.